morning, afternoon, maybe evening even, math people. So today we're going to be looking at, we're not going to do a hand-drawn quadratics or hand-drawn cubics per se, as finding regression for that is a bit more complex, but we are going to do an example of linear hand-drawn graphs. Takes us back to a little bit of grade 10 work that we did way back. So we'll be just reviewing that a little bit because in case we have to do a hand-drawn graph sometime with linear graph skills. So I'm popping open the board here. That's what we're going to do today. We'll do an example like that. The other thing that we'll do is we'll get into some of the sine and cosine. That's the sine and cosine and maybe even tangent graphs that come up and how they work. And that'll be the last part or the second part of this unit in the functions and the graphs. We're not going to do the log or exponential function graphs here. Instead, we're going to focus on the sine, cosine ones, or as they like to call them, the sinusoidal function graphs. And that'll be next after we're done this section here. Anyways, let's get to what we're going to do today. And today we're going to do a hand-drawn graph. So some graph paper around might be handy for you. So we're just going to look at today on whatever day it is here. Let me look what day it is. I forget already. This will be the 6th day of this unit, day 6. And this is day 6. And we're going to be looking at plotting a linear graph. Okay. So we're going to be doing, we're going to be hand plotting the graph. Okay, we're going to be looking at the slope and line equations. Oops. Review. And we're going to do an example or two. And that's probably what we'll do today. So some graph paper being handy is a good idea. So let's start off with just reviewing the slope and the line equation. So if we have a regular type graph, say we'll just sketch it out, say here's our axes. We're not going to bother with the squares. If we have a regular type graph where we have our x, where's my marker? There it is. Okay, we have our y here and our x here. Okay, so if we have a linear graph and we state it like, we'll use an arrow here. Okay, so let's say our linear graph is here. Okay, and this flat graph, slope is 0. Going down, slope is negative. Going up like this, slope is positive. So if we have a graph that looks like that. Okay, and let's say we had 2 points on the graph. Okay, first of all, this here is little b, and that's our y-intercept. Value. Okay. So the general equation for this line, the linear equation, is given by y equals m, which stands for slope, x, which is this variable here that varies along the line, plus b, Obviously, y is this variable here that varies along vertical. Okay. This is our y-intercept. And this represents our slope. And the xy is any point on the line. Okay, so that's our general linear equation. So how we get slope is our next equation that we need. Slope, on the other hand, is the rise over run. So if you have this point here, which we'll call A, and this point up here, which we'll call B, it kind of makes a triangle like this. So you can look at it as this rise, as it starts here and goes up over this run, is one way to look at it. And they do have a formula for that in algebra. If you name this point point B and that one point A, you could say that slope is equal to YB minus YA, which is the rise of the line, over XB minus XA. And that's how we get the slope of the line. Okay? And we're going to calculate a linear regression line with the help by hand, but with the help of these two equations. Okay? Now, you can also do the A first and then the B second. It doesn't matter, as long as you keep the same location. B's have to be here, A's have to be here, or put the A there and the B there. Okay, as long as you keep it in the same way. Okay, so that's our slope equation. You know, and these are the X and Y points of these 2 points up here. Okay, so let's actually do an example of linear plotting some results, and then do a linear regression line, do an extrapolation, do an interpolation, and that's what we'll do today. Okay, and I know that we use Desmos a lot for the curves that we did, and also for the linear part, but once in a while, it doesn't hurt us to know what we're doing by hand, because we have to be able to, rather than have the computer figure out our spacings, we have to do that on our own. So it is good skill. So let's go ahead and do an example of this. So I got some data here. So let's say following data of time versus distance traveled. Okay. Let's say the following data is of plot the graph okay. We're going to put time on the X. Plot the graph and find the following and answer the following. Okay, so the first thing we're going to do is let's say plot the graph. We're going to do that, and then the first thing we're going to do is we're going to find the linear regression line of the data. Now, not everybody's going to get the same linear regression line, because we may draw it in a slightly different spot when we do our best fit line. Okay, so keep that in mind. When you do it by hand, it's going to be slightly different probably. So, but it'll be close though. Okay, then let's say interpolate the distance at, let's say, what am I going to use here? Let's say 7 seconds. Or no, that's too easy. Yeah, let's go 7 seconds. Okay, and then extrapolate using the linear regression line. Extrapolate with the linear regression line the, let's say, distance when the time is, let's go out of our way, let's say 30 seconds. Okay, so here's our data. We've got time in seconds here, and distance traveled by the object. And meters, we'll say, over here. So the first one we got, okay, 2, 7. Next one we got is 4 and 10. There's 6 points here that we're going to plot. 8 and 16. Then we got 12 and 22. Okay, then we've got 16 and 28. And then finally 20 seconds, 20 seconds and 34. Okay, so I'm going to do this on graph paper on the next page, but I'll let you write that down first. Then we're going to find the linear regression line. Then we're going to interpolate and extrapolate our axis. Everything's going to be done by hand. We're going to use the help of our linear slope equation and our linear line equation to get that y equals mx plus b. We're going to find out what b is. We're going to find out what slope is. And then we'll be able to plug those in to give us our line. And again, like I said, depending on how you draw your line and how you graph, yours might be slightly different than your neighbor's kind of idea. Because you're doing it by hand, you're not using Desmos, which has a technique that it uses to get your linear line of regression. Okay, so let's go on to the next page here. Okay, and I'll flip back and forth for our data. Let's put up some graph paper. Okay, so I'm going to get the graph paper out. Graph paper in here. Okay, so let's see. Let's see, medium grid. That looks okay. Small grid might be too small, I think, yes. Let's go with medium here. Large grid's probably too big. Let's see. That's probably not enough graph paper. That's not giving us enough. Let's go back to graph paper here. Yeah, that's better. Okay, so what we're going to do is we're going to make our axes here. I'm going to leave a little bit, and then we're going to kind of look at what we need for our spacing and how we do that. Now, when you're doing it by hand and you got a whole piece of graph paper, it's a good idea to use a large amount of your graph paper. Count how many vertical and how many horizontal spaces you have. Divide your maximum number by that, and kind of each space will be worth that amount or something close to that amount. You do some rounding in there. Let me demonstrate. Okay, let's make my grid here. It's going to be a little bit smaller because of my picture being so small. You might have some more spaces. Oh, let's go to a black line here. There we go. Okay, this is going to be my vertical axis there. And my horizontal axis is going to be here. Okay, now if we count this out horizontally, I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 2, 4, 6, 8. I got 28. My biggest time is 20. So if I go 1 per square, I should be okay. Okay, so I'm going to take my marker and I'm just going to mark in every 2 as 2 seconds up. So we should put this in. Okay, we'll go with black here. I'll use skinny writing so I can fit everything nicely. Okay, got a 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20 is where our graph ends. And that's good for me because it's close to the end of my graph. And I could have probably, I'll put a couple extra ones on here. And this is time. And it's in seconds. So we got to label our axis as well. Okay, then we look at our distance. Our biggest distance in the table is 34. So we want 34 close to up here, right? And I've got 2, 4, 6, 8, 10, 11, 12, 14, if I count that very top one, which is kind of pushing it a little bit. But if I take 14, if I take 34, which is my biggest number, and I divide by 14 spaces on the vertical, in my calculator, I get 2.42 per space. So you want to round up. So if I go like every space is 2.5 meters, that means my biggest value is going to be of 34 is going to be close to this top. Okay, so one space 2.5, 2 spaces are 5. Well, that's a nice round number. So we'll go 5, go up another 2, 10, go up another 2, whoops, 15, go up another 2, 20, go up another 2, 25, go up another 2, 30, okay, and then obviously 35 is going to be up here, very top line. Should have left a little more space. Okay, so that's going to give us our distances, and now we can plot our points on it. And of course, we should probably label this as distance. In meters. I'm going to plot this in green, so it's a different color. I'm going to go ahead and plot the lines that we had. So we have to look back what we had as a result. Okay, just reminding us, 2 and 7, 4 and 10, and so forth, up to 20 and 34. So we're going to plot all of these 6 points now. 2 and 7. So 2, now each one of these is 2.5. So this would be 7.5 here, so about there. Okay. The next one that we have is 4 and 10. Well, 10 and 4 are right on both lines, so about there. Okay. We then look 8 and 16. Well, both of those, 8 is here, 16. Okay, that's 2.5. That's 3/4. Well, it's going to be just below that, 8 and 16, both there. Okay, then we have 12 and 22. 22 would just be about there. That's 22.5, so about here. Okay, we can see the linear relationship showing up. 16 and 28. So 28, that's 27.5 right there. So that's 25 And then 2.5 more is 27.5 because each one is 2.5. So just a little bit above that, like that. And our last one is 34 and 20. So 20 and 34. So it's going to be just one below there, so maybe about here. So there's our data points on our graph. So now we can do our best fit line. So I'm going to use the drawing tool to do that. You will use a ruler if you're doing it by hand. So I'm going to use the straight line tool. And I think I'm going to put it as green as well. Okay, so let me see if I can get it here. Looks to be, okay, let's see if I can get it best fit. So you want to kind of hit, that one's a little low. I'm going to move it up a little bit. This one here, I can try to get most of the dots or leave some below it and some high. That would be wrong because there's a bunch too high. Okay, there's a couple below there, maybe a little lower. Okay, that looks pretty close depending on my graph. So there's my best fit curve. Okay, put my best fit curve in. I guess we could have a title for this. If we were doing titles, there might be one for the graph, but in this case, I'm just going to say this is distance versus time. Okay, for our graph. Okay, so now we want to get into the math part, finding the linear regression line. So the first thing we want to do is we want to get a slope. Now, when we're calculating slope, we need 2 points on the line to calculate the slope to use that formula. Or we could do rise over run. We could draw a triangle, but it's not a good idea to use a point that's a data point. Don't pick this point and this point, even though you know what they are, in case they're errors. Okay, so it's a good idea like to find points that are right at junctions. So there's one right at a junction here. This one's at 6 and 10, 12.5 because it's right in that corner. So I'm going to star these in blue. So I'm going to take this point and call it our A point on the graph. Then up here, I'm going to look for where they are close to 2 lines here. To get a slope here. Well, we could do it here, but I want more space. That one looks like a 11 and 20 right there. Well, I'm going to do it right there. What the heck? Now yours might be different spots. So now what we do is we kind of read what these would be. This would be 6 seconds at 10, 12 and a half. So this one is 6 and 12.5. This one is 11 and 20. Remember, the X point goes before the Y point. Okay, so there is, now we're going to do the slope of this. So our next step is to get the slope because we're going to need that when we're trying to figure out y equals mx plus b. And we kind of can figure out what b is here as well if we look at it, or we could calculate it. Both work. So let's do the slope. Slope equals yb minus ya all over xb minus xa. Okay, so in our case, yb is, oops, I was going to put 11. 20, right, because it's a y point. 20 meters minus ya, which is 6 meters, okay, divided by 11 seconds minus, oh, what am I doing? This is 12.5 meters. Sorry, guys. Can't read. If you were confused there, that's good, because I made a mistake. Okay, so y is 20, y down here 12 and a half, 12.5 meters. Okay, then it's 11 seconds minus 6 seconds. There we go. That's better. Okay, so we take out our calculators or just work it out, depending on what we have. So 20 minus 12 is 7.5 meters. And then 11 minus 6 is 5 seconds. So 7.5 divided by 5 seconds. So let's see what we get. Okay, I get 1.5 or 3 over 2 if you like fractions. It's 1.5. So that's our slope. Meters per second. Actually, the speed of this, if you know physics. Okay, but that is our slope. Okay, so now there's two things we can do. If we can find B and look here, and this is 2.5, so this might be crossing here at around 4, right? So we could say, oh, the y-intercept looks like a 4. Then we can write out if we can find and get it accurately by our graph, we can say, okay, this B value, which is equal to the y-intercept, we can say that looks like it equals 4, approximately. Okay, or we could calculate it as well. So if we did that, we could write our linear regression line. Y equals mx plus b. Okay, so now we know what the slope is. We leave y and x blank. Y equals the slope, 1.5, x plus 4. So here's our linear regression line. I guess in this case, it's not really regressing, it's growing. But it's our line of best fit. Okay? And this is our equation. Now, that's if we can find the y-intercept and kind of identify it. If we can't find the y-intercept, there's another thing we can do. Okay? If we weren't, let's say we didn't trust our eyes and saying that's 4, maybe it's 3.5, I don't know. You could calculate it by picking a point on the line like this 4 and this 10, plugging in 4 here, 10 there, and the slope there, and calculating B. Let's try that. Okay, we'll do it underneath. Okay, alternatively, if you can't see the y-intercept, you can calculate it. Okay, so choose a point. On the line. Okay, so the point I'm going to choose 410. And plug it in with slope and calculate B. Which is our y-intercept. So here's what it would look like. We're going to start with y equals mx plus b. We're going to plug in 10, 4, so 10 for y, 1.5 for m, and 4 for x. Okay. Okay, so let's do our calculation here. Okay, so we're going to go 4 and 10. Okay, so 4 times this, 1.5 is our first step. I'm just double checking, make sure I put the right point in. Okay, so 1.5 times 4, that's 4, 5, 6. Okay, subtract 6 on both sides. Oh, good, we guessed right on. So we can say, okay, we're very confident in this. That looks right. Okay, so you can calculate it or you can kind of read it. Okay, so now let's answer our 3 questions. Our 3 questions, if we go back to the example, are find the linear regression line. We did that. Okay, so the linear regression line that we found was y equals 1.5 x plus 4. Okay, interpolate the distance at 7 seconds. Interpolate the distance, so we can put in a 7 to figure out what it would be, or we could look at the graph. Let's do y equals, this is b, y equals 1.5, put in the 7 seconds, plus 4. Okay, 1.5 times 7 we have to do. So that's 10.5 probably, but let's double check. 10.5 plus 4. Okay, that would equal 14.5 meters is what we have. So that answers that one. So let's check on our graph and see if we got about 14.5 meters at the 7-second mark, just to see if it works. Okay, so 7-second mark is here. 14.5 meters. Yeah, that looks pretty good. There's the 15. That looks like about half a meter there on our scale. Okay, and the last one is to use it. We're going to extrapolate way past here at 30 seconds. So that one we have to use the equation. We'll do it over here because we can't use a linear regression line, and the distance is 30 seconds. Okay, so we want the distance, which is still y. So 1.5 times 30 plus 4. Okay, 1.5 times 30 is 45 plus 4. So this distance, I'll move that up because I might be in your way there. This distance is then going to be y equals 49. So therefore, it's 49 meters at 30 seconds. Okay. Now, we can't do a double check on that one unless we made the graph big enough, right? So on Desmos, we just kind of scroll around and we could see it. But when we're doing it by hand, if it's not big enough, we'll have to trust that we have the proper regression line in there. So that is basically how we do it by hand. Okay, so let's summarize what we did here. Okay, what we did was we need the slope equation, which is y1b minus ya over xb minus xa, and the line equation, y equals mx plus b, which we did use with Desmos anyway. We need to know those equations for a line equation for a quadratic and equation for a cubic equation, obviously. Okay, and then what we did was we just basically took our results from the graph here first, and we plotted them on a graph. But before we did that, we kind of divided how many spaces we had on the vertical by our max number to see what each space would be worth, and then we rounded up to something reasonably close to that, so that our biggest number would be up near the top. Same thing with the time. We had some extra time in there. Then we plotted our graph. Okay, once you plotted our graph, we chose 2 points on it that were not data points and found the slope using yb minus ya divided by xb minus xa. Then, once we had the slope, we then looked to identify the y-intercept, or if we can't identify the y-intercept, we could take a point of data, plug it into y equals mx plus b with the slope that we calculated, and work out what b was. So you could do it that way, or you could identify it on the graph if you're confident in your ability to read what it is. And then this would be our linear regression line, which answers our last two questions. You can use this linear regression line to plug in what the time value or the x value was when they asked for us to predict it at 7 and 30 seconds. And that's where we figured out those two questions. And that's basically how we do hand-drawn linear regression. Okay, so you can do a hand-drawn linear regression line. Now, when I give the assignment, I don't mind if you do it by hand, if it's a line. If it's a curve, you could even do a curve by hand, but they're a little harder to find the linear regression curve. If you have a curve, for example, let's say if we were doing a quadratic and we had something that looked okay, I'm just going to do a quick one here. This is just a okay, so let's say we had this line here. There we go. Okay, so let's say we had some data here, and we had to use quadratic regression. If we had something that looked like this, I have to use a pen here. And it might be quadratic regression. It's much harder for us to find the equation here because fitting it into there and calculating everything, we know that a quadratic, you don't have to write this stuff down. Has three things for us to find out, and the only one that we would know from the graph is this, right? So calculating these would be much more difficult. So when we have a quadratic one, if I ask you to predict, say if this was 2, 4, 6, 8, 10 time seconds, and I had, let's say 10, 20, 30, 40, 50, and 60 meters there. So if we were doing this by hand, and I said, what is the value at 5 seconds? We would have to use just basically interpolate the data using lines to identify where it is, like this. Okay, we wouldn't be able to necessarily, if we can't figure out the linear regression or quadratic regression line in this case, we would go, okay, well, I take a straight line tool, make it into dots here, or dashes. Okay, and I go 5 seconds here. That's going to be about right there. Okay, and you can say, oh, that's 15 meters. Okay, so you can do it this way as well, right on the graph. Okay, and we've done some of that in science, obviously, and other math classes like grade 10. Okay, so I just wanted to do one example of linear regression because you can do that one by hand, and it will be, one of those things that you could be asked to do it by hand rather than use Desmos. But I won't ask you to find a quadratic or cubic regression line by hand. I'll be asking you can use some technology, either graphic calculator or Desmos. So you can do that on the assignment. If you want to do the graphs on Desmos as well with the linear lines, that's good too. That if you want to do them by hand for the linear lines, we now know how to do that. Okay, so let's check our time here in terms of my recording. I don't even know. I didn't even look at it yet this morning. So let's take a look here. Oh, that's almost 40 minutes. So we better stop there today. Okay, next day we'll get into the quadratic, or we'll get into the sinusoidal curves a little bit. Okay, so we'll see you tomorrow.